Imagine stumbling upon a galaxy so mathematically improbable that its mere existence feels like a violation of cosmic law. A flawless golden sphere suspended in space, wrapped by a perfect shimmering ring of young blue stars, all separated by a vast empty void that should not exist. Nothing about it fits any model. Nothing about it makes sense. And yet there it is, 600 million light-years away, hanging in the darkness like a cosmic joke aimed directly at our understanding of how galaxies form. This is Hoag's object. A structure so clean, so symmetrical, so deliberately arranged that the deeper astronomers stare into it, the stranger it becomes. It looks less like something shaped by gravity and chaos, and more like something designed. The story begins in 1950, when Arthur Hoag, working at the Palomar Observatory with a 48-inch Schmidt telescope, spotted a faint, unassuming blur on a photographic plate. At first, he thought nothing of it. The night sky is full of odd shapes and faint wisps of light. But something about this one pulled at his attention. A bright, circular ring wrapped around a compact, luminous core. He wondered if it might be a planetary nebula, the dying breath of a star shedding its outer layers. But the ring was too wide, too bright, and the core looked suspiciously like a miniature galaxy. Hoag documented it carefully, noting the object's position in serpens, but he lacked the tools to investigate further. The photograph entered his 1950 publication as a curiosity, not a discovery. Little did he know he had captured one of the most perplexing galactic structures ever found. For decades, Hoag's object lingered at the edges of astronomy like an unanswered riddle. Most galaxies are messy. Spirals twist unevenly, arms clump and smear. Ellipticals are diffuse and lopsided. Irregular galaxies look like cosmic accidents. But this looked like someone had drawn a galaxy with a compass. A glowing inner core, a perfect circular gap, a luminous ring, with nothing at all connecting them. By the 1960s and 70s, more powerful telescopes and early spectroscopic measurements confirmed the truth. This wasn't a planetary nebula. It wasn't a trick of perspective. It was a galaxy, and a massive one. The light's redshift placed it 600 million light-years away, meaning that the ring itself spans tens of thousands of light-years across. No planetary nebula could ever mimic something on that scale. Hoag had unknowingly discovered a new category of galactic phenomenon. As technology advanced, the mystery deepened. Throughout the 1980s and 90s, improved CCD imaging revealed that Hoag's object didn't match any known galactic type. It wasn't a spiral. There were no arms, no bar, no disk. It wasn't an elliptical. The ring was too bright, too sharp. It wasn't a typical ring galaxy either. Most ring galaxies are formed through violent collisions that leave scars. Tidal tails, debris clouds, lopsided shapes. Hoag's object had none of these. No wounds, no deformation, no history of chaos. It was pristine. Then came the Hubble Space Telescope in 2002. Its high-resolution image stunned the astronomical community. The golden core was unmistakably elliptical, dense, old, and smooth. The outer ring glowed a bright blue, filled with young, hot stars. And between them lay a dark, eerily empty moat, as if the galaxy had been sliced apart with surgical precision. Even stranger, in the background of the same Hubble image, was a smaller ring galaxy. A bizarre coincidence that astronomers still joke about today. The symmetry of the ring is one of its most astonishing traits. When astronomers measure its circularity, they find deviations so small they might as well not exist. In a universe governed by chaotic forces, gravity, turbulence, dark matter instabilities, such perfection should be impossible. Ring galaxies born from collisions are uneven, clumpy, rippling with asymmetry. The Cartwheel galaxy, for example, is a sprawling wreck compared to the mathematical beauty of Hoag's object. In every known example, collisions leave fingerprints. But Hoag's object is spotless. Some scientists considered whether gravitational resonance might be responsible, similar to how Saturn's moons shepherd its rings. But Hoag's object has no known companion to sculpt such a structure. Others suggested perhaps our view is unusually perfect, that we are looking almost directly face-on. Statistically, that's rare, like flipping a coin 10 times and getting heads every time. Computer simulations attempted to reproduce the ring through collisions, mergers, and exotic dark matter halos. Every attempt failed. The models produced rings that were lopsided, dusty, uneven, or oval. None could recreate the smooth symmetry of Hoag's object. Spectroscopy added even more intrigue. Not only is the ring perfectly shaped, its stars move in remarkably consistent orbits. The symmetry is not superficial. It is encoded into the galaxy's motion itself. That level of uniformity suggests either a long period of uninterrupted isolation or a formation process unlike anything we understand. At the center, the golden core paints its own mystery. Packed with ancient stars, chemically rich and long past their prime, it behaves like a small, elliptical galaxy that has lived a quiet, uneventful life for billions of years. Yet somehow, it ended up embedded inside a brilliant ring of young, newly formed stars. The age gap between core and ring is enormous. Their chemical fingerprints differ. Their rotational patterns differ. It's as if the two structures were born in entirely different places and somehow fused together into a single system. But if that happened, where is the damage? Why does the core look untouched? Then there is the gap, the empty dark void that separates ring from core. In typical ring galaxies, this region is filled with debris, tidal streams, distorted gas clouds, leftover stars from the collision that triggered the ring. In Hoag's object, the space is silent, empty, unnaturally clean. A cosmic no-man's land tens of thousands of light-years wide. Some suggest it is maintained by orbital dynamics, like an invisible forbidden zone where stable orbits simply cannot exist. Others believe a long-dead central black hole may once have blasted this region clean, though there is no evidence of such activity today. The few faint stars found there don't resemble either the core or the ring. They appear older, more primitive, like fossils from an earlier galaxy that once lived here before being erased. For every hypothesis, there is a contradiction. A collision would explain the ring, but not the pristine core or the lack of debris. A resonance would explain the symmetry, but not the absence of a bar or disk. Gas accretion would explain the youth, but not the perfection of the ring. Dark matter could shape the structure, but only if arranged in highly unusual ways. And then there is the galaxy's location. Hoag's object lives in cosmic solitude, far from dense galaxy clusters or bustling galactic neighborhoods. It exists in a quiet region of the universe where interactions are rare, mergers are unlikely, and disturbances almost non-existent. Its solitude may have preserved its symmetry, but it also makes its formation even harder to explain. Hoag's object is a contradiction in every direction. A perfect ring without a collision, a youthful structure wrapped around an ancient heart, a galaxy with an empty interior where stars should be, a system that looks engineered despite being, as far as we know, entirely natural. In a universe built on chaos, Hoag's object is order incarnate, a quiet, impossible shape suspended in the dark, defying everything we thought galaxies could be. Some astronomers suspect that Hoag's object owes part of its impossible beauty not to what surrounds it, but to what doesn't. It lives in a region of space that is unusually empty, a low-density stretch of the cosmic web sometimes called a void. Out there, far from the crowded cityscapes of galaxy clusters, interactions are rare, collisions are unlikely, and intergalactic gas drifts more slowly, undisturbed by the endless pulling and tearing that defines denser environments. In such a quiet place, gas falling toward a galaxy might not be stripped, shocked, or shredded. Instead, it could slide in gently from all directions, settling into a nearly symmetric orbit around the core. In theory, that kind of calm infall could help create a circular ring as clean and ordered as the one we see around Hoag's object. But that picture is still more imagination than proof. The details of how such a process would work remain mostly guesswork, and no simulation has yet managed to reproduce a ring this perfect under such serene conditions. What seems more likely is that the galaxy's remoteness has helped preserve whatever weird structure formed there long ago, freezing it in place for hundreds of millions of years. In busy clusters, even a beautifully formed ring would soon be warped by the gravitational pull of nearby giants, stretched, twisted, and eventually erased. Hoag's object, by contrast, appears to have enjoyed the luxury of near-total cosmic peace. No neighboring behemoths to tug at it, no frequent flybys to shake loose stars or tear at its gas. Its isolation might also explain why the core has remained so pristine. Without a swarm of small galaxies feeding it fresh material, without gravitational harassment stirring the pot, the central elliptical could sit quietly for billions of years, smooth, dust-free, and stable. A fossil from an earlier era, preserved like a dinosaur bone in the cosmic desert, now surrounded by a ring that formed much later in a way we still don't understand. But the loneliness that protects Hoag's object also makes its formation more puzzling. Isolation removes the easiest explanation, a recent collision. If there are no stones at the edge of a pond, you have to ask what created the perfect ripple. Astronomers have spent years surveying the space around Hoag's object, hunting for clues. A faint stream of stars far beyond the ring, the battered husk of a dwarf galaxy, a shredded remnant drifting nearby. So far, nothing conclusive has appeared. When Hubble took its famous high-resolution image of Hoag's object in 2002, one particular detail made jaws drop. Nestled inside the outer ring, just beyond the golden core and far in the background, was a smaller, fainter, ring-shaped galaxy. A second ring, a background twin. It's not physically connected to Hoag's object, not bound, not part of the same system at all. It's far behind it, so distant that the two galaxies will never meet. And yet, from our perspective, the smaller ring appears perfectly framed within the gap of the larger one, as if the universe had composed the shot for aesthetic impact. It's almost theatrical. A ring galaxy in the foreground, and a second ring galaxy seen exactly through the empty moat between core and ring, aligned so precisely that a shift of just a few arc seconds would have hidden it completely. Mathematically, the odds are absurd. Ring galaxies are rare to begin with. The chance of one lying directly behind another along our line of sight is microscopic. Seeing them aligned in such a visually striking way is like flipping a coin and having it land on its edge twice in a row on different sides of the table. This double Hoag sightline has fueled both serious statistical work and playful speculation. Astronomers know that from a physical standpoint, this is likely just coincidence, a random alignment in a vast universe where improbable things still happen. But for the public imagination, the image became iconic, a symbol of hidden repetition in cosmic patterns, a hint that maybe ring structures are more common than we think. merely waiting in the depths for us to look closely enough. Scientifically, the background twin is frustrating. It's so faint and distant that even Hubble can only show it as a small, blurry loop of light. Spectroscopy is hard, the signal is weak, and its true nature remains uncertain. It might be a genuine ring galaxy. It might be a galaxy whose center is obscured by dust, creating the illusion of a ring. It might even be influenced by gravitational lensing. For now, it remains a tiny echo in the background, a visual reminder that our view of the universe is governed not just by physics, but by chance. And yet, even this coincidence has potential value. The light from the background twin has to pass through the outskirts of Hoag's object, its ring, its halo of gas, maybe even its dark matter envelope. In principle, subtle distortions or absorption features in that light could reveal additional information about the material surrounding Hoag's object, turning the twin into a natural probe, a cosmic backlight shining through the galaxy we're trying to understand. If the geometry and alignment of Hoag's object are strange, the ages of its stars are even stranger. At first glance, the color contrast is clear. The core glows warm and golden, the signature of old, low-mass stars that have burned steadily for billions of years. That part fits expectations. Elliptical-like cores typically host elderly stellar populations, long past their star-forming youth. But the ring is completely different. Its brilliant blue color comes from massive, hot stars that live fast and die young. Some of them are only a few million years old. Spectroscopic studies confirm this visual impression. When astronomers split the ring's light into its component wavelengths, they find the fingerprints of very young stars, less than 10 million years old, mixed with older ones that might be a few 100 million years old. That tells us the ring has been forming stars for an extended period and is still actively doing so today. The core, by contrast, shows no sign of recent star formation. It's been dormant for billions of years. In a typical galaxy, you see more of a gradient. Older stars in the center, younger populations farther out, with a continuous transition between them. But in Hoag's object, there is a sharp break. A dead heart surrounded by a vibrant halo of youth, with a nearly starless mote in between. It's as if two different galactic timelines have been overlaid without any of the intermediate history. This age paradox raises a fundamental question. Where did the ring get its fuel? Young stars need dense, cold gas to form. That gas had to be collected in the ring somehow. In many galaxies, such gas arrives through interactions, tidal stripping from neighbors, mergers with gas-rich dwarfs, streams of material funneling inward or outward. Hoag's isolation makes those explanations less likely. There are no obvious donor galaxies nearby, no wreckage, no tidal tails. One possibility is that the galaxy slowly accreted gas directly from the intergalactic medium. Hydrogen drifting through the void could have been pulled in over hundreds of millions of years, settling into a circular orbit around the core, where it cooled enough to collapse into new stars. That might explain the ring's ongoing youth, but it still doesn't explain its extraordinary symmetry. Gas inflows are usually clumsy. They produce warped disks, irregular structures, and asymmetries, not a pristine, uniform ring. Another idea is that Hoag's object once consumed a gas-rich dwarf galaxy. Its stars would have been absorbed into the core or scattered, while its gas settled into a ring around the center and ignited star formation. That could account for the ring's youth and its different chemistry. But again, we're missing the debris. No faint stellar streams, no distorted core, no visible scar. The ring's metallicity, its content of elements heavier than hydrogen and helium, adds another layer to the puzzle. The core's stars are metal-rich, as expected from an old population that has gone through many generations of star birth and death. But the ring's stars are less enriched. They're not primordial, but they do carry a different chemical signature, as if their gas had a separate history. If the ring gas had simply come from the core, pushed outward somehow, its metallicity should match the core's enrichment. Instead, the ring looks like it formed from fresher material, gas that had been processed in a different environment before arriving here. And within the ring, the metallicity is surprisingly uniform, just like its shape. In most galaxies, chemistry varies with radius and direction, reflecting complex histories of inflow, outflow, and feedback. Hoag's ring seems chemically mixed in a way that suggests a gentle, thorough blending before stars began to form, without leaving behind the turbulence we would normally expect. Structurally, Hoag's object refuses every easy category. It has no spiral arms winding from its center, no bar cutting through the core, no dust lanes tracing hidden patterns in its light. Spiral galaxies, the most familiar type in the nearby universe, are defined by twisting arms shaped by density waves. Regions of higher gravity that move through the disk, compressing gas and igniting star formation. Hoag's ring is not an arm bent into a circle. It sits detached, a separate, nearly perfect loop that has no visible physical bridge to the core. The core itself is an almost textbook, elliptical smooth, featureless, made of old stars, with no evidence of the bar structures that so often form naturally in disk galaxies. In most systems, if you erase the arms, you still see scars, asymmetries, faint streams, shells, bulges. Hoag's object is clean, too clean. Most galaxies are messy beneath the surface. Zoom in with enough resolution and you'll find lopsidedness. One arm brighter than the other, a dust lane cutting across one side of the core. A faint trail of stars leading into intergalactic space from a past encounter. Hubble's image of Hoag's object, however, shows almost none of these irregularities. The ring's brightness is impressively uniform. The core's light falls off smoothly in all directions. The space between them is almost perfectly empty. It's as though someone took a chaotic galaxy and stripped away everything that didn't fit a simple, symmetric design. Some researchers have wondered if this order is the result of an unusually stable distribution of mass, possibly shaped by a smooth, spherical dark matter halo that prevents the formation of bars and spiral arms. Yet, even that doesn't fully explain why the ring exists while the interior remains vacant. The ring's symmetry is so striking that it's become a calibration tool. If software can trace Hoag's ring as an almost perfect circle, working with it correctly, astronomers know their algorithms are behaving. That level of precision is profoundly uncomfortable in a universe where gravity, gas, and time constantly disrupt structure. Rings are not static sculptures. They are collections of stars and gas in motion, subject to internal instabilities and external tugs. Even without a neighbor to disturb it, the galaxy's own uneven mass distribution should, over billions of years, distort the ring. Stretch it slightly, warp it, turn the circle into an ellipse, and yet, as far as we can tell, the ring has remained almost perfectly circular and evenly thick. To keep it that way, the gravitational potential it sits in must be extraordinarily symmetric. One idea is that Hoag's object is embedded in a very smooth, nearly spherical dark matter halo. That would create a uniform gravitational pull in all directions and allow stars to follow stable, circular orbits at a specific radius, carving out the ring. But dark matter halos are hard to measure, and the rotation data we do have make this scenario more complicated, not less. In most galaxies, rotation curves reveal the unseen hand of dark matter. Stars in the outer regions move faster than visible matter alone can explain, indicating a hefty, invisible halo. Hoag's object does not follow the script perfectly. The velocities of stars in the ring aren't quite as high as expected for a galaxy of its apparent mass. Its rotation curve hints at a dark matter halo that may be weaker, oddly shaped, or truncated in ways that don't fit standard models. And yet the ring, which should be especially sensitive to gravitational quirks, is stable and uniform. Some astronomers suggest that instead of having less dark matter, Hoag's object might have it distributed in a highly unusual configuration. Perhaps a halo with a very sharp inner edge, or a flattened shape that creates a gravitational sweet spot at the ring's radius, while making the gap region dynamically hostile to stable orbits. In that scenario, matter that ventures too close to the core would eventually be expelled or fall inward, leaving the interior clean. More speculative ideas dip into modified gravity theories that tweak the rules of how gravity behaves at very low accelerations, potentially reducing the need for dark matter. Hoag's object, with its odd rotation profile and perfect ring, is exactly the kind of anomaly that provokes such hypotheses. But so far, none of these alternatives have provided a complete, satisfying explanation. Dark matter, modified gravity, peculiar halo geometry, each can solve part of the puzzle. But none can account for the whole picture without hand-waving or fine-tuning. Beyond invisible mass, there's the invisible gas. Radio observations reveal that Hoag's object is wrapped in a halo of neutral hydrogen gas that extends 2 or 3 times farther than the bright ring. That in itself is not unusual. Many galaxies have extended gas envelopes. What's unusual is how calm this one seems to be. In most actively star-forming systems, halos are dynamic. Gas falls inward to feed star birth, while stellar winds and supernovae blow material back out, creating complex flows. In Hoag's object, the hydrogen halo appears smooth and largely motionless, with no strong signatures of inflow or outflow. The gas isn't obviously streaming into the ring to fuel its young stars, nor is it being blasted away. It sits there like a ghostly shell, stable and quiet. If the ring is still forming stars, it must be receiving gas somehow. Maybe in tiny, undetectable trickles. Maybe through processes too subtle for our current instruments. But again, we run into the same contradiction. To form the ring, something unusual had to happen. To preserve it, almost nothing has happened since. Metallicity measurements add more nuance. The gas that formed the ring isn't pristine. It's been enriched by previous generations of stars somewhere. It contains oxygen, nitrogen, iron, and other heavy elements. Not as much as the core, but enough to prove that it didn't come directly from untouched primordial hydrogen. Yet we don't know where that enrichment occurred. In another galaxy? In a long evaporated dwarf? In a distant part of the intergalactic medium? Each option comes with new inconsistencies. Every answer spawns a new question. Even the motions in the core refuse to behave exactly as expected. In many galaxies, the inner and outer regions share a common rotational story. Bulge and disk, bar and arms. They all participate in the same general spin. In Hoag's object, measurements hint at a subtle but important decoupling. The core and ring do not seem to share the same rotational behavior. The ring rotates like a disk, its stars moving in orderly, nearly circular orbits around the center. The core, however, appears dynamically different, with a slower or at least differently oriented spin, as if it retains the memory of some older, separate system. This kinematic mismatch reinforces the idea that core and ring are not just different in appearance, age, and chemistry. They are different in origin. Two histories locked together in one frame, orbiting the same center of mass, yet telling utterly different stories about how they came to be. Hoag's object doesn't just challenge one piece of galactic theory. It pokes holes in many of them at once. Its isolation undermines collision models. Its symmetry resists our understanding of gravitational chaos. Its age distribution breaks the expectation of smooth stellar evolution. Its dark matter profile refuses to conform to standard halos. Its gas halo is too calm. Its metallicity is too uniform and too different from the core. Its core and ring move like strangers forced to coexist. Put simply, this galaxy is wrong in all the most interesting ways. And that is why astronomers can't stop looking at it. In an imperfect universe, Hoag's object is almost too perfect. And somewhere inside that perfection, hidden in the gap between what we see and what we can explain, lies a clue to a chapter of galactic evolution we have not yet written. If the ring had grown naturally as an extension of the core's original disk, its rotation should have been tied to the core's own spin, with the inner mass acting as the gravitational anchor that sets the rhythm for everything beyond it. But that's not what Hoag's object reveals. The ring rotates faster than the core, as if it's responding not to the weight of the luminous center, but to something larger, something broader, perhaps the galaxy's dark matter halo rather than the stellar core itself. That difference in rotational behavior suggests a fractured history, a system assembled from mismatched parts that never quite grew into one another. The core moves like an ancient elliptical, slow and steady, while the ring whips around it like a younger, lighter, more agile structure. If Hoag's object began as an old oval-shaped galaxy and later captured a vast supply of external gas, the mismatch in spin suddenly makes sense. The original core keeps its sluggish, fossil-like rotation, while the newly formed ring settles into a faster orbit, dictated by the galaxy's larger gravitational skeleton. What makes this even stranger is the smooth transition between the slow-spinning core and the fast-spinning ring. In galaxies with mismatched dynamics, the intermediate regions often twist, warp, or buckle as two different rotation regimes fight for dominance. Yet Hoag's object has none of that. The space between the core and the ring is almost completely empty, like someone carved out the middle of the galaxy with a cosmic scalpel. This emptiness isolates the motions of core and ring, preventing them from interacting strongly enough to synchronize their spins. They orbit together, but live separate dynamic lives, bound by gravity, but untouched by each other's movement. Astronomers have suggested that the slow rotation of the core ties into its strangely pristine appearance. In most galaxies, gas slowly drifts inward over billions of years, feeding new star formation, stirring the central regions, and adding angular momentum. But Hoag's object seems deprived of such inflows. Almost all of its gas resides in the ring and the extended halo, leaving the core to evolve in quiet isolation. Without fresh gas to torque it, the core's rotation stagnates, remaining as slow as it likely was billions of years ago. Even the galaxy's hypothetical black hole, if one exists at the center, appears starved. Many galaxies show radio or X-ray activity from matter falling into their central black holes. Hoag's object has almost none. The silence may be the result of the core's slow spin, which fails to channel gas inward efficiently. No fuel, no fireworks. There is also the lingering possibility that the core wasn't always this slow, and that we are catching Hoag's object in the middle of a long transition. If the ring formed recently on cosmic timescales within the last billion years or so, there simply hasn't been enough time for gravitational tugging between core and ring to bring their spins into alignment. Over the next few billion years, as faint interactions accumulate, the core may gradually speed up, drifting closer to the ring's dynamics. Or perhaps not. Hoag's isolation may preserve the slow spin indefinitely. With no nearby galaxies to exert external torque, the system may remain locked in this asymmetric, decoupled configuration forever, a fossilized heart surrounded by a youthful, vibrant halo. The ring itself is equally perplexing. Most galaxies experience starbursts because something triggers them. A collision squeezes gas into dense clouds, or a close encounter funnels gas inward, igniting waves of rapid star formation. But Hoag's object shows none of the usual signatures of such events. And yet, its ring is full of hot, short-lived O and B-type stars, the cosmic equivalents of fireworks. They burn intensely and die quickly, meaning the ring is continually producing them. Star formation is not only ongoing, it is vigorous, but nothing appears to have set it off. There are no tidal tails, no distorted arcs, no debris from a recent merger. The galaxy is isolated. Even the faint background twin seen in Hubble's picture is far behind it, with no gravitational influence. The question is simple. If the ring is forming stars so energetically, where does the gas come from, and what started the process? One explanation is that the ring's gas has been sitting there for a long time, slowly condensing until it finally crossed the threshold required for star formation. But if that were true, we would expect the ring to show signs of gradual depletion, with activity fading unevenly across its circumference. Instead, the star formation is remarkably uniform. The ring appears self-sustaining, almost as if it found a way to keep itself alive. New stars and supernovae send shockwaves rippling around the ring, potentially triggering further star formation in adjacent regions. This feedback loop could maintain the ring, but only if the structure was already arranged perfectly to sustain such cyclical activity. We then confront another contradiction: the metallicity of the ring's gas. The gas has relatively low levels of heavy elements, suggesting it came from a less enriched source, perhaps external to the galaxy. Low metallicity gas cools less efficiently, making star formation harder, not easier. Yet Hoag's object is somehow coaxing this stubborn gas into forming stars at a steady rate. The ring behaves like a machine that shouldn't work, but somehow does. The dark matter halo might offer part of the explanation. If the halo is unusually smooth and spherical, it could create a gravitational environment in which gas naturally settles into a ring, where even small instabilities or density waves become enough to compress the gas into stars. In this view, the ring is not powered by violence, but by balance, forming stars through gentle, long-term processes rather than catastrophic events. Some astronomers have even speculated about a hidden companion, an ultra-faint dwarf galaxy passing through the ring, invisible to current instruments, sending out ripples that compress the gas without disrupting the symmetry. It's possible, but without evidence, it remains a ghost hypothesis. Another hypothesis invokes resonance. In some galaxies, rings form when stars and gas settle into orbits that resonate with a central bar or spiral pattern. Saturn's rings, sculpted by its moons, follow similar principles. But Hoag's object has no bar and no spiral arms. For resonance to work, something must provide periodic gravitational nudges. Perhaps a long-vanished intruder once passed nearby, setting up oscillations that outlived the encounter. Or perhaps the dark matter halo itself contains subtle irregularities that impose resonant orbits on the stars and gas. Simulations can produce resonance rings, but not rings as perfect as Hoag's. The structures that form in models tend to be warped, clumpy, or uneven, unless the initial conditions are fine-tuned to an implausible degree. In the early decades after its discovery, some astronomers wondered if Hoag's object wasn't a ring galaxy at all, but a gravitational lens, an Einstein ring produced by a massive foreground object, bending light from a background galaxy. It certainly looks the part. A luminous central mass with a perfect circle of light around it. But spectroscopy ruled out this idea decisively. The ring and the core share the same redshift, meaning they are at the same distance. A background galaxy would show a higher redshift. The ring also contains well-defined star clusters, not the stretched arcs typical of lensed galaxies. And the core does not have enough mass to produce such a lens. The lensing hypothesis died quickly once real data arrived. The deeper astronomers look, the stranger the galaxy appears. Even radio observations contribute to the mystery. Ring galaxies with active star formation typically emit strong radio waves from supernova remnants and cosmic ray production. Hoag's object is almost silent. The radio emissions are barely detectable, far weaker than expected for a ring bursting with young, massive stars. This suggests one of two things. Either the ring is forming fewer massive stars than it appears, or something is suppressing the usual chain of events that produce radio waves. One possibility is a weak magnetic field. Cosmic rays spiral along magnetic field lines, generating radio emissions. A weak field would allow them to escape quickly. Another possibility is that the ring's gas is unusually diffuse in certain regions, preventing cosmic rays from being trapped long enough to radiate. Whatever the reason, the radio silence adds another layer of strangeness. A galaxy forming stars loudly in visible light, but whispering in radio wavelengths. Then there is the ultra-smooth core, one of the most pristine galactic centers ever imaged. It lacks dust lanes, gas clumps, or young star clusters. Even elliptical galaxies usually show some irregularities, minor scars of past interactions, faint traces of dust, slight asymmetries. Hoag's object does not. The core is a near-perfect sphere of old stars, so evenly distributed that it almost looks artificial. This suggests that the core has been untouched for billions of years, sealed off from the energetic processes happening in the ring. The empty moat between core and ring acts as a permanent quarantine, preventing gas from drifting inward and forming new stars. The result is a perfectly preserved relic of an earlier cosmic era. The outer ring itself is a marvel of dynamics. A massive, thin loop of stars and gas orbiting at hundreds of kilometers per second should not remain stable for billions of years, without constant disturbances making it warp or dissolve. But the ring holds. Its rotational speeds are remarkably uniform. The gravitational pull of the dark matter halo probably plays a crucial role, providing a stable environment where orbits can stay circular. Gas collisions within the ring help maintain order by damping out irregularities. Star formation feedback may distribute gas evenly, preventing clumps from dominating. The isolation of the galaxy prevents external tugs that could warp the ring. Everything about the environment conspires to preserve the structure. And yet, even with all these stabilizing factors, simulations struggle to reproduce anything close to it. Computer models, despite decades of refinement, repeatedly fail to create a galaxy that matches Hoag's object. Rings produced in simulations warp or distort. Gaps fill in. Cores become dusty or elongated. Metallicities don't match. Rotation profiles diverge. Dark matter distributions that stabilize rings cause problems elsewhere. Every time a simulation solves one part of the puzzle, it breaks another. The galaxy exists at a strange intersection of parameters, too symmetrical to be a collision remnant, too chemically distinct to be internally generated, too stable to be a transient structure, too isolated for a recent disturbance. It fits no known category of ring galaxy. It is neither a classic impact ring, nor a resonance ring, nor a polar ring. It is simply itself. Hoag's object rejects the chance alignment theory as well. The core and ring share the same redshift and rotational alignment. The ring's dynamics show it is gravitationally bound to the core. The empty gap is truly empty, not a projection effect. A background galaxy would produce distortions or mismatched spectral signatures. The probability of perfect concentric alignment is astronomically low. Chance alignment simply cannot account for the observed data. Finally, spectroscopy reveals one of the sharpest contrasts in the entire galaxy. The core's light is dominated by old stars, showing deep absorption lines and no recent star formation. The ring's spectrum bursts with emission lines from hydrogen and oxygen signatures of hot young stars and glowing gas. The chemical enrichment of the ring is intermediate, not primordial, not recycled from the core, suggesting an origin outside the main body of the galaxy. The core and the ring not only look different, they are different. In age, in motion, in chemistry, in behavior, in history. Every wavelength we use to study Hoag's object tells us the same thing. This galaxy is a puzzle assembled from mismatched pieces that nonetheless form a flawless whole. A system that should not exist, yet somehow does. A contradiction wrapped in symmetry. A galaxy that looks like a cosmic symbol perfect, serene, impossible. And the deeper we look, the stranger it becomes. The fact that the core and the ring move at different speeds is one of the most unsettling details hidden in Hoag's object's light. When astronomers split its glow into spectra and measure the Doppler shifts, they're essentially listening to the galaxy's heartbeat in different places. In most galaxies, that heartbeat transitions smoothly from the center outward. The inner regions and the outer disk are connected in one continuous dynamical system. But in Hoag's object, there's a sharp break. The stars in the ring orbit much faster than the stars in the core, and the two regions don't seem to be dynamically coupled the way we'd expect. It's as if the heart and the halo are following different sets of instructions. If the ring had simply grown outward from the core's own disk, their motions should be closely linked. The core's gravity would anchor the ring's rotation, and the speeds would transition smoothly. Instead, the ring seems to be moving under the influence of something larger. The galaxy's broader dark matter halo. The core, slow and compact, behaves like the remnant of an old elliptical galaxy, while the ring behaves like a younger, faster disk orbiting the overall mass distribution. That fits a picture in which Hoag's object began life as an elliptical galaxy, then later acquired or organized gas into a ring that settled into its own orbital pattern. What makes this even stranger is how cleanly separated the two regimes are. In many galaxies where misaligned or decoupled components exist, there's a transition zone in between, a messy region where orbits twist, stars cross, and structures distort. Hoag's object has no such blur. Between the slow-turning golden core and the fast-moving blue ring lies a dark, almost empty gulf. The gap itself acts like a buffer, preventing the two components from exchanging angular momentum and locking into a common pattern. They're part of the same galaxy, bound by the same gravity, and yet they rotate almost as if they belong to different systems that never quite touch. That slow spin may be the key to the core's eerie stillness. In most galaxies, gas gradually sinks inward over billions of years, bringing fresh material to the center, spinning it up and feeding central star formation or a hungry black hole. In Hoag's object, nearly all of the detectable gas is concentrated in the ring and extended halo. The core appears cut off from this supply line. No gas flowing in means no new stars, no dust, no violent feedback, and no mechanism to torque the core into a faster rotation. It simply turns at its own ancient pace, like a fossil locked at the center of a much more active shell. If there is a central black hole, as there likely is, it too seems starved. Hoag's object is quiet in X-rays and radio wavelengths. There are no jets, no outbursts, no signs of recent feeding. The black hole, if present, may be one of the most well-behaved in the nearby universe, sitting in a gravitationally calm, dust-free environment with almost nothing to eat. Over cosmic time, the ring and core could slowly trade angular momentum and drift toward a more unified rotation pattern. But the galaxy's isolation means there is nothing external to hurry that process along. We may be catching Hoag's object in a rare, intermediate state, where two histories are still clearly visible and have not yet blended into one. That brings us to one of the biggest paradoxes in this system. The ring is in the middle of a starburst without an obvious trigger. In most galaxies, bursts of star formation have a clear cause. A smaller galaxy plunges through a larger one, compressing gas and igniting clusters of new stars. Or a gravitational encounter with a neighbor stirs gas inward, piling it up into dense regions where stars are born in furious waves. These events leave marks: distorted arms, tidal tails, shells, and knots. They are messy, loud, chaotic. Hoag's object's ring, however, is building massive, short-lived O and B-type stars with none of the usual fingerprints of chaos. Spectra of the ring show all the signs of vigorous star formation: strong hydrogen emission lines, hot blue stars, and energized gas. But there are no obvious scars, no debris streams, no lopsided density, no intruder galaxy lurking nearby. Even the smaller ring galaxy seen in the famous Hubble image is far behind Hoag's object and has no gravitational connection to it. The neighborhood is empty and quiet, yet the ring is burning brightly with newborn stars. One explanation suggests the ring's gas has been in place for a very long time, orbiting quietly until subtle processes began coaxing it into stars. But if that were true, we might expect star formation to taper off as the gas is gradually consumed. Instead, the activity seems distributed, as if some mechanism keeps gas available and spread along the ring. Another idea paints the ring as a self-sustaining star factory. In this picture, as new stars form and then die as supernovae, their shock waves travel along the ring, compressing nearby gas and triggering the next generation. The structure's own geometry might help those waves circulate, creating a feedback loop that keeps star formation going without a fresh external jolt. This would be a delicate act. The gas in the ring is relatively low in heavy elements compared to the core, making it harder to cool and collapse. Under ordinary conditions, such gas is reluctant to form stars. Yet Hoag's object is managing it anyway, and doing so in a configuration that hardly changes the ring's shape. Whatever is driving these starbursts isn't explosive and short-lived. It's quiet, persistent, and weirdly orderly. To understand how such a ring could form at all, some astronomers turn to the idea of resonance, the way repeating gravitational tugs can corral matter into specific orbits. In many galaxies, resonance rings form when a central bar or spiral pattern pumps energy into certain orbital radii, causing gas and stars to accumulate in rings. It's the same underlying physics that shepherds Saturn's rings into clean edges under the influence of its moons. But Hoag's object has no bar, no spiral pattern, nothing obvious inside that could act as a driver. So the resonance, if it exists, would have to come from elsewhere. Perhaps a long-vanished dwarf galaxy once swept past, tugging just hard enough and just long enough to lock material into a ring before drifting away into the dark. Or maybe the dark matter halo itself has a subtle asymmetry, guiding stars and gas into a preferred radius. These ideas are compelling and mathematically plausible. But for now, they remain speculative. And even when simulations try to mimic this, they almost always end up with rings that are a bit off, slightly warped, slightly uneven, or short-lived. There was, for a time, a more straightforward idea. Maybe Hoag's object isn't peculiar at all. Maybe it's an optical trick. From a distance, a golden center with a perfect ring of light around it looks suspiciously like an Einstein ring, a classic signature of gravitational lensing, where a massive foreground object bends the light of a more distant background galaxy into a circle. That would have been a neat, clean explanation. No exotic formation, just curved space-time. But spectroscopy killed that dream quickly. The ring and the core share the same redshift, meaning they're at the same distance. They are not background and foreground. They are one system. The ring also isn't stretched and distorted the way lensed images usually are, and the central core doesn't have nearly enough mass to produce such a large, bright Einstein ring. The lensing explanation evaporated, leaving us face to face with the fact that the ring is real, physical, and orbiting around that quiet core. Spectroscopy, which was supposed to resolve the nature of the galaxy, instead deepened the mystery on nearly every front. The core's spectrum is exactly what you'd expect for an old, metal-rich, quiescent elliptical. Strong absorption lines, very little hot gas, no signs of recent star formation. The ring's spectrum looks like another world entirely. Hot, blue stars, bright emission from ionized gas, and a metallicity signature that doesn't match a simple origin story. It's too enriched to be pristine intergalactic gas, but too different from the core's chemistry to have simply been pushed outward. It belongs neither entirely to the galaxy's interior, nor to the untouched void beyond. Even the history written in the ring's stars is confusing. Spectral analysis suggests at least two distinct waves of star formation there. One relatively recent, within the last billion years, and another further back in time. That means the ring has not just flickered into existence and started forming stars once. It has been active, quiet, and active again, all while the core remained essentially frozen. Whatever is feeding the ring's star formation seems to act in cycles, but without the violent companions or cluster environment that usually drive such long-term behavior. If optical light and spectra show us a galaxy that's split in two, infrared observations drive the point home. In most galaxies, infrared images reveal hidden dust and cool stars in the core, the lingering remnants of past activity and inflows. Hoag's object's core is nearly dark in the infrared, as smooth and empty of dust as it appears in visible light. It's not just quiet now, it seems to have been quiet for a long time. The ring, however, lights up in infrared. Beneath the glaring blue of young stars is an older, cooler population, invisible in optical images, but obvious at longer wavelengths. The ring isn't a new feature. It's home to stars that have been aging there for a long time. Patches of warm dust reveal small, localized regions of current star formation, hidden in optical but glowing in infrared. Little embers scattered around a seemingly uniform halo. Taken together, these observations imply that the ring has a layered history. It's not just a single event frozen in place. It's a structure that has hosted multiple generations of stars, each adding complexity to its chemical and dynamical story. Infrared observations also verified that the gap between core and ring is truly, deeply empty. If faint, older stars or dusty filaments were hiding there, infrared cameras should have picked up their glow. Instead, the void remains almost completely dark. The separation is real. it isn't caused by dust blocking our view or by a projection effect. It's an honest, physical mote between an ancient stellar sphere and a star-forming ring. All of this feeds into one of the strangest parts of the story: the orbits themselves. When astronomers map how fast stars and gas move around the galaxy, they expect certain patterns. In a simple system, rotation curves trace the balance between visible matter and dark matter. Deviations from those curves point to interactions, disturbances, or unusual mass distributions. In Hoag's object, the ring stars broadly follow what you'd expect for a galaxy of its size, but with subtle, systematic oddities. Speeds wobble gently along the ring instead of hugging a perfectly flat curve. Orbital paths are almost unnaturally circular, and the ring remains razor-thin over billions of years. In simulations, that combination is extremely hard to maintain. Tiny gravitational nudges, random gas flows, or the slow drift of dark matter are usually enough to thicken and distort rings. Yet in Hoag's object, the ring seems locked into place. Even the vertical motions of stars, the way they bob above and below the galactic plane, are apparently suppressed or damped to an unusual degree. The picture this paints is of a galaxy whose dark matter halo is not only massive, but incredibly smooth and symmetric, shaping space in a way that keeps the ring in an exact, stable lane. With so many anomalies stacked on top of one another, some astronomers have floated a bold idea. Maybe Hoag's object is not a modern galaxy caught in a weird phase, but a relic of a much earlier cosmic era that somehow survived mostly unchanged. In the first few billion years after the Big Bang, the universe was more violent and chaotic than it is today. Galaxies formed rapidly, merged often, and burned through their gas in intense bursts. Most of the galaxies we see now are products of that long, turbulent history, the end states of countless collisions and rearrangements. But what if Hoag's object formed in a quieter corner of that early universe, in a region with fewer neighbors and a particularly smooth patch of dark matter? It could have settled into its ring and core configuration early on, and then been left largely untouched while the rest of the cosmos evolved around it. The core's properties support that idea. Its stars are old and metal-rich, suggesting an early, intense period of star formation that later shut down. The ring's chemistry indicates gas that has been processed but not heavily disturbed, enriched over time but not repeatedly churned through mergers. Viewed this way, Hoag's object might be one of the rare survivors of an ancient galactic archetype that was common in the distant past, but almost never preserved to the present day. If that's true, then its symmetry makes a different kind of sense. Over eons, random irregularities and orbital quirks can be ironed out as stars and gas settle into the deepest parts of the gravitational potential. A galaxy that has been stable for billions of years has had time to relax toward a more idealized state. Small asymmetries fade. Orbits circularize, structures smooth out. The ring we see today might be the end result of a long, slow relaxation process that required not just the right initial conditions, but also an almost uninterrupted cosmic quiet. But even this ancient relic picture leaves big questions unanswered. How did that ring form in the first place? How did the galaxy acquire the gas with the right metallicity, arrange it at just the right radius, and then keep it there? Why does the ring still have enough gas to be actively forming stars now? These questions lead to another uncomfortable realization. Statistically, a galaxy like Hoag's object should almost never exist. Astronomers can estimate how rare various galactic features are by surveying large samples of galaxies. Ring galaxies alone are rare, roughly 1 in 1,000 in the local universe. Perfectly smooth, symmetric rings are rarer still. Add in a dust-free elliptical core, a huge empty gap, a stable, non-expanding ring, an isolated environment with no neighbors, mismatched stellar ages, and unusual dark matter behavior. And the odds of all these traits coinciding start to drop off a cliff. Even if we're cautious and avoid simply multiplying probabilities, the fact remains. Every time we add a constraint, perfect circular symmetry, lack of tidal debris, chemical mismatch between core and ring, extreme isolation, anomalous rotation curves. Hoag's object looks more and more like a statistical outlier, sitting far in the tail of the distribution. It's the kind of object that standard models would predict we might never actually see, even if the universe were teeming with ordinary galaxies. And yet, there it is, not only existing, but flaunting its improbability with a background galaxy perfectly framed in its central void, like a cosmic bullseye. That little background galaxy, uncovered by Hubble's zoomed-in images, is itself a reminder of just how peculiar the system is. It has nothing to do with Hoag's object dynamically. It's far behind it, at a completely different distance. But from our vantage point, it lies almost exactly in the middle of the ring, just where you'd put it if you were composing an image for maximum effect. It doesn't help explain the ring, the core, or the gap. It simply adds one more layer of "really?" to an already unlikely arrangement. When scientists step back and ask whether tidal forces, hidden mass, or slow evolution might eventually tear this configuration apart, simulations often predict that rings like this should be fragile. Without material in the gap to help stabilize the gravitational field, the ring ought to be more vulnerable to small perturbations, whether from the cosmic web, tiny unseen companions, or even the slow reshaping of the dark matter halo. Over hundreds of millions of years, such forces tend to smear out structures, warp rings, or pull them inward. Yet Hoag's object sits there, apparently unwarped, unbroken, and unbothered. The galaxy's mass distribution only complicates things further. Rotation speeds indicate there is plenty of mass in the system. And yet when astronomers tally up the visible light, gas, and expected dark matter, the numbers don't quite line up in the usual way. Hoag's object seems to occupy a strange middle ground, not dark matter dominated enough to match standard halos, but too massive and too stable to be explained by visible matter alone. The missing mass might lurk in faint stars we can barely detect, in cold gas invisible at standard radio wavelengths, or in an unusually shaped dark matter halo that concentrates extra mass right where the ring needs it. None of those possibilities fit comfortably within our current models, but all of them hint at physics we don't fully understand. Given all this, it's natural to ask, could this be a temporary arrangement? Are we just lucky, catching the galaxy in a brief phase before it changes into something more ordinary? Maybe the ring is slowly collapsing inward or drifting outward and will eventually dissolve into a more typical disk. Perhaps the current configuration is a fleeting snapshot in a much longer story. That idea is attractive because it explains the improbability. If the configuration is short-lived, fewer galaxies will be caught in it, which means it would be rare to see one. But the observed stability of the ring works against this. There is no obvious distortion, no measurable expansion, no clear indication that the ring is in the act of falling apart. If this is transient, it is not obviously so. The galaxy gives us no obvious countdown clock, and that is where the scientific frustration really sets in. In most cases, as instruments improve, mysteries become less mysterious. Better maps, sharper images, and richer data tend to funnel us toward a consensus. Hoag's object has stubbornly resisted this trend. Every new data set tightens the constraints, but none has provided the single decisive clue that would let one theory triumph over the others. Collisional models explain some traits, but contradict others. Resonance models capture aspects of the ring's stability, but not its origin. Relic scenarios fit the ancient core, but struggle with the ring's youth and activity. No explanation wins outright. In that sense, Hoag's object has become more than just a peculiar galaxy. It's a stress test for our theories of galaxy formation and evolution. If your model can account for spiral arms, mergers, starbursts, and ring galaxies in general, that's good. But if it fails completely on Hoag's object, then there's still something missing in your understanding of how matter and gravity shape the universe. Maybe future telescopes will finally break the deadlock. Deep, high-resolution mapping of its dark matter halo. Sensitive radio surveys of its cold gas. More precise spectroscopy of its faint outer regions. Perhaps somewhere in that data will be the smoking gun. A subtle warp, a hidden stream, a pattern in the motions of stars that points clearly to one formation history. Or maybe not. Maybe Hoag's object will remain what it currently is. A quiet, golden heart floating inside a flawless halo of blue, hanging alone in the darkness of a cosmic void. A galaxy that seems to have taken everything we think we know about galactic structure and arranged it into a configuration that almost never should have happened. And then held that pose for billions of years. It's easy to look at something this strange and want a neat answer. A single line in a textbook. Hoag's object is an example of X, formed by Y, maintained by Z. But right now, it's a reminder of something more humbling. The universe is not obligated to be simple, or to match our expectations, or to fit comfortably inside our equations. Sometimes it creates objects that exist at the edge of our understanding, and just leaves them there, daring us to keep trying. Somewhere, 600 million light-years away, that perfect ring is still turning, slowly carrying its blue stars around an ancient golden core above a dark, empty gulf. Whether it's a relic from a different era, a brief transition, or a galaxy built through a pathway we haven't yet imagined, it stands as a quiet challenge written in starlight. We like to think we're close to grasping the big picture of how galaxies live and die. Hoag's object whispers back, not yet. And if you enjoy wandering through these unresolved questions at the edge of what we know, there are many more cosmic enigmas waiting. Like, subscribe, and share your own theories in the comments. Because somewhere out there, beyond the familiar spirals and ellipticals, the universe is still hiding galaxies that refuse to make sense, only on beyond horizons.